Right, this is A21 January 2010, and this is from the new spec. So there are two papers that year, an old specification one and a new specification. So this is question 3. Define angular velocity for a body moving in a circular path. And angular velocity is the rate of change of angle moved through. You can of course say theta over t provided you define both of those. An object rests on a horizontal turntable which rotates at a constant angular velocity. The object may be displaced from the centre of the turntable along a radius to any displacement s is shown. So as it moves round, this mass, say it was a penny, will move further and further out. On the axis of figure 3.2, sketch graphs to show the variation of angular velocity with its radial displacement and the variation of acceleration. Now I have these written in already. We're told that it rotates at a constant angular velocity, omega. We have two equations for A. So A is omega squared r, or A is equal to v squared over r. But the one which is a constant in it is A is omega squared r, so we're going to use it. And therefore A is proportional to r, so we get a straight line through the origin. Omega, we're told, doesn't change, and therefore omega with the change of omega with the displacement s is going to be a straight line. Mine's not too straight long, I'm going to straighten it up here a wee bit. So that's a nice straight line there across. So omega is constant. Part C, and again I have some answers written in. A jet aircraft completes a circular turn of radius 600 metres in a horizontal plane when flying at a constant speed of 153 ms to the -1. Calculate the angular velocity of the aircraft. So V is equal to R omega. We know that V is 153 and R is 600, so you just manipulate the equation and you end up with an answer of 0.255 radians per second. I'll scan in a wee bit so you can see it a bit better. Calculate the acceleration of the aircraft, so you just use A is equal to omega squared r, and that's just our omega value from up here squared multiplied by the radius, which is 600 metres, and it comes out as 39.02 ms to the -2. State the direction of the acceleration of the aircraft. It is of course towards the centre, so the same direction as the centripetal force. Part 4, the pilot of the aircraft has a mass of 75 kilograms. Calculate the restraining force of the pilot's harness needed to keep him stationary in his seat. And again, a very straightforward calculation. F equals mv squared over r. 75 times 153 squared over 600 gives you 2,926 newtons.